Hello and welcome to another video, this time on sketching and transforming graphs, the solutions to that. Students don't tend to like graph sketching, but really it's because there's so many different techniques depending on what the shape of the equation is. But if it's quadratic, naturally you want to, if possible, factorize it first. So I'm going to factorize this one quite casually. You can do the 2 times minus 15 is minus 30 and find two numbers that add to give 7 and times to give minus 30. It would be 10 and minus 3, by the way. But I'm just going to plonk down the answer, I think, here, or try to anyway. I think if I've got plus 5 here and minus 3 there, it works. That's how I always used to do it when I was younger, but you can do the more systematic approach. Anyway, how does that help me sketch it? Well, we can just then go, okay, sorry, it's such a dodgy sketch. It goes through 1.5 and minus 5. And it also hits the x-axis at minus 15. Now, with these ones which factorize, they don't tend to care about writing down the minimum vertex. It's when they don't factorize that you might want to know the minimum vertex so you can show something about the graph. So that should be fine. Okay, for B, this is a straight line. And once you realize that, it's real easy to say when x is 0, y needs to be 3. So I know it hits 3 on the y. But when y is 0, x needs to be minus 4.5, something like that. And then I can just draw it, maybe smarten that up a bit so it's clear that that is a 3. I knew it. So it goes through minus 4.5 and 3 in the x and y axes. So they should be easy. This one, try and factorize it again. It's a little bit awkward to factorize. Personally, I'd do this if I was going to factorize this. And then I go, okay, so y equals the minus of plus 6 minus 2. And so we can see it goes through minus 6 and positive 2, but it's upside down. So minus 6, positive 2, upside down. Oh, not really very much to scale. But also when x is 0, y is 12. So you've done it. There we go. That is a sketch of that quadratic. Okay, D is a reciprocal curve. And anything of the form k over x is going to look something like this, provided this number at the top is positive. And that's because you can see this, like, when x is 4, y is 1. But then when x gets really, 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 really big, y gets tiny, because 4 divided by a million is a tiny number. On the other hand, when x is really, really small, close to 0, like 0.1 or 0.01, suddenly you've got 40 or 400 for y, and that's why when x is small, y is getting bigger. And likewise, when it's negative, it's just a really similar graph. So that's all you need for that one. It doesn't intersect the axes. E is a bit more tough. Now, generally speaking, 1 over x squared would look like this, yeah? Try and find a similar graph in your head, which you know what it looks like, and then you can do it. Now, 2 over x squared is just going to look exactly the same, but it's going to be stretched. When you put a minus, that makes all y coordinates go from positive to negative. In other words, y is definitely going to be negative there for any x value. And so what that does is reflect it in the x-axis. And so actually, it's going to go down like this. Now, they did ask, actually, I've just seen the question, they did ask to label asymptotes. So let's just quickly point out that on here, the asymptotes were the x and y axis, which is x equals 0 and y equals 0. On here, it's just the y axis, which is an asymptote. And so that's the line x equals 0. We're done. Okay, cool. Looking good so far. What do we got next? We've got a cubic. Okay, let's factorize it. Take out the 2x. You're going to have x squared plus x minus 12, I think. And we can factorize that again to give y equals 2x times x plus 4x minus 3. Okay, I can now sketch this cubic here, the f cubic, because it's simply going to be like this. It's going to go through, now cubics, when they're the right way up, or if you like positive x cubed, they always look like that. If it was a negative x cubed, it would always look like this, some kind of shape like that. And so our one is positive x cubed, so that's the right way up, and it's going through 0, -4, 0, and 3. So -4, 0, and 3. That's supposed to be going through the origin. Label it. Put the y and x on, and that will do for your sketch. Okay, G. Okay, we've got a quartic here. Can you see it's x squared times x times x? So that's a quartic, but it's already factorized, which is nice. So, oh, got a thinking, loss of servo or something. Let's just see if that goes away in a second. It normally does. Maybe Zoom is just fed up with how much I've been using it today. I don't know. Oh, it's come back. There we go. Okay, so quartics. Quartics, positive x to the 4s normally look like that. Negative x to the 4s normally look like that. You can work this out, by the way, the behavior at infinity, because when x is very, very large and infinitely big, y is going to be infinitely large. Same when x is negative, because to the power 4 it becomes positive, and it works the other way around for that one. So we know it's going to have that general shape. Okay, so let's draw it. Now, what have we got here? We've got repeated roots. A repeated root at -1, but then it goes through 2 and 5, and we know it's of that general shape. So I think it's going to go something like this. It's going to touch at -1. It's going to go through 2 and back through 5. They're not symmetrical, these ones. That's a common misconception that they need to be symmetrical. We can also find the y-axis intercept, or just label those. We can find the y-axis intercept because we just set x equal to 0. That'll give you 1 squared, which is 1, times by -2, times by -5, which is +10. So you can find that y-axis intercept. Okay, h. This looks like one which doesn't factorize, so completing the square would be a good idea, just so we can say something about what it's looking like. Now you'd have -4 plus 9, which is +5. And so for h, you're going to have the following. Move it 2 across, 5 up. Its lowest point is at 2, 5, but it also goes through 9 on the y-axis. And you've got, you've said a bit more about the curve then. It's got a line of symmetry at x equals 2. There's a line of symmetry there. Quadratics are the only ones which like kind of have to be symmetrical. Okay, so what are we on now? I. Okay, factorizing this will be funny because students don't like factorizing this kind of stuff. You're going to have 8 minus x. So it's a cubic, but it's got a repeated root at 0 and it goes through 8. I'm going to try and sketch this just in here, this one. Getting a bit messy on this board, apologies. But it's an upside down cubic as well. So rather than going something like that, it's going to go the other way around and come down, touch at 0, and then go through 8. So that's I call them upside down cubics. Basically, when it's a minus x cubed, then it's upside down. So it looks like that, I. J, minus 3x to the 4. This is an interesting one because you might be forgiven for thinking that all quartics look like that or the M upside down, but that's not the case. Yeah, and this is what makes it difficult. Graph sketching's fine, but it's one of those topics where there's always exceptions to any kind of rule you try and make up. So think of just x to the power of 4 for a second. X to the power of 4 looks really similar to x squared, it's just steeper. Yeah, it looks like that. That's y equals x to the power of 4. 3x to the power of 4 will just look like that, except steeper. And minus 3x to the power of 4, well, that's where the y coordinates go from positive to negative. And so this one's just going to look like this. It has no, only one turning point. It doesn't have like 3 like they can have. It has only one. And yeah, so that one's going to look like that. Okay, k, 5x plus 2y is 8. Let's do k. That's clearly a straight line. So I'm going to use my straight line trick, which is where I say when x is 0, y is 4. And when y is 0, x is 1.6. Then you just draw a line through them. That's how I do the straight line ones. They're really not that bad. Okay, what have we got next? We've got y equals 1 over x minus 6. This will cause a few problems, I reckon. Y equals 1 over x minus 6. Now, think about what y equals 1 over x looks like, because it's been transformed to y equals 1 over x minus 6. In other words, x has been replaced with x minus 6, which moves this graph 6 to the right. That makes loads of sense because you always get asymptotes where you divide by 0. You always get vertical asymptotes when you divide by 0. So we know that there's 1 on this graph at x equals 6. The curve is undefined when x is 6, if you like. But it's just like the 1 over x graph, but it's been moved to 6 to the right. Yeah? Can we find out the y-intercept? Yeah, just let x equal 0, and you'll see y is minus a 6. So that's minus a 6. And that's that one done. And we've got the equation, the asymptote as well. Okay, just 4 more to go on this mammoth graph drawing bonanza. Let's see if I can just rub some stuff out. Give myself a bit more space. Quite a long question, this one, it has to be said. Okay, so M. Right, this one, I'd probably take that out first. And then I get a bit upset because I can see that doesn't factorize. Well, let's complete the square. So leave the minus outside. X plus 3 squared minus 9 plus 10. Well, that's plus 1. Yeah? So if I plug the minus back in, I can't plug it into that bracket, but I can make it minus 1 on the end. What I can now see is that that is a quadratic, and it's upside down. And at minus 3, when x is minus 3, y equals minus 1. So minus 3 minus 1. I think it's going to look something like that. Minus 3 minus 1. And what's more, when x is 0, y is minus 10. So that occurs at minus 10, that intercept. And you've got it. Y and x. What are we moving on to now? This one. So this is just like the graph of y equals 2 over x, but we've moved it up 3. That's what we've done here. That's a function transformation where you move it up 3. So once again, let me just give myself some more space. Down here maybe this time. What we've got here, we're just going to take 2 over x, which would look like something like that. Yeah. But now we're going to move it up 3. So if it's moved up 3, suddenly it's gone asymptote at y equals 3. And you can see it makes loads of sense because when x gets super, super big, like thousands, millions, billions, y is roughly 3. It's just slightly bigger than 3. So it's going to look something like this. And now when x is, when y is 0, what is x? Well, if you rearrange this, you're going to get minus 3 is 2 over x. And so x is minus 2/3. And so that must be minus 2/3 that point. And you've done it. Okay, I should point out that the y-axis, which is the line x equals 0, is also an asymptote there. Just 2 more to go. What have we got here? Okay, that looks like a perfect square to me because that looks like 2x minus 1 squared if I was to factorize that. 4x squared minus 2x minus 2x, which is minus 4x and 1. Yeah, that's good. This one, if we park that minus outside here, we can make it 2x squared minus 7x plus 3. And then does that factorize? Let's have a look. Hopefully. 3. So if I have minus 3 minus 1, yeah. Okay. Also, we've actually got a repeated cubic factor. Now, let me tell you something. You will always get a stationary point of inflection if you've ever got brackets cubed, yeah, or odd-powered brackets, actually. That's going to have the effect of generating a stationary point of inflection at x equals a half, because they are, that's actually minus 2x minus 1 cubed. Notice as well that it's a minus x to the power 4, so it's probably going to have that kind of shape. It's almost certainly going to have that kind of shape. And it goes through a half but it doesn't actually go through it. It kind of levels off at a half, but then goes up again and comes back down through 3. Yeah, because you've got a repeated factor and it's a cubic repeated factor, which gives you a stationary point of inflection there. That's very hard to see. Also, when x is 0, I think you can see y is going to be -3 there, and we've got all of it. But that was a tough one, that one. Students will find that really tricky. Hard to get that one right. Okay, p, 9 minus x to the 4. This doesn't look too bad. Let's give ourselves a bit more space. Where can I do this one? Oh, I'm doing this all over the page at the moment. You can see I'm quite a messy mathematician. Sorry about that. Okay, let's just try and factorize this. Well, this is difference of 2 squares. But then we can kind of use difference of 2 squares again, because that's like √3 minus x, √3 plus x. And there's no such thing as the sum of 2 squares, so we can't do anything with 3 plus x squared. It's an irreducible quadratic. And so what have we got here? We've got a quartic, and it's going to go through √3 and minus √3. It's an upside down quartic as well. And so it's going to look something like this. Messing up a bit here. Something like this. √3. Now you might think, why doesn't it have like 2 bumps in it? Well, it's just because think of x to the 4. X to the 4 is the exception. It just goes like x squared straight up. Well, if you reflect it, making it minus x to the 4, then it's going to look like that. And then you're just going to add 9 to it. And so it just moves it up. So it goes through 9 on the y. So, you know, loads of bits can catch you out on these kinds of questions. They really can. Watch out for them. They're tough. They're really tricky. Okay, let's keep going. What do we got here? We've got a graph. Brilliant. And they're showing us a sketch, and it passes through 0, 3, 1, 0, and 4, 0. Sketch on separate diagrams this curve. Okay, that just moves it to the left one. And so that's just going to go like this. That's the function transformation we're using there. So that's now 3, 0, and that's now 0, 0. That's going to stretch it, the original function, that is. And so we're doubling all the y coordinates. That doesn't do anything to the x coordinates. And so that's just going to be 0, 6. But otherwise, it's going to be at 1 and at 4 still. Part C, well, that is a squash scale factor 2, which is, sorry, a squash scale factor 1/2, which is a stretch scale factor 2. So all the x coordinates are going to double there. And so what you're going to have for that one, 0, 3 is still the same, but we're going to need to double all our x coordinates. So that's now at 2, and that's now at 8. And it's done. What have we got next? 3 and 4. Okay, right. F of x is x squared. The point a minus 3, 9 lies on f of x. The curve f of x is translated 3 units in the positive x direction. Okay, firstly, if you're translating it 3 units to the left, that means that it's suddenly become x minus 3 squared. And is stretched in the y bar scale factor 4. Write the equation of the curve after these transformations. Okay, y equals 4 times x minus 3 squared. Cool. Find the coordinates of A under these transformations. Okay, we'll just plug in x is minus 3, and we'll find what the new y coordinate is. Or if you like, just move it. No, it's probably easier to do it like this. Let's call it A dash. We need to move it 3 to the right, so that's now at 0. And then we need to stretch it scale factor 4 on the y, so that's 0, 36. We're just quadrupling the y coordinates. Okay, this one, a little bit different. Okay, we're stretching it in the x direction, scale factor 1/2, and translating it 5 units in the negative y direction. So scale factor 1/2, that's if you're stretching it scale factor 1/2, that's the same as multiplying it by 2x, and then translating it 5 units in the negative y direction. That means we need to put on a minus 5, so we get y equals 4x squared minus 5. A dash will be, well, we need to halve the x coordinates, so minus 1.5, and then increase the y coordinates, decrease coordinates by 5, so that's going to be minus 1.5 and 4. Cool. Okay, number 4. I seem to remember this one's quite awkward. Okay, we've got to sketch these graphs. So this is move 5 to the right and stretching the y by 2. So that's going to be at 2, 0. Oh, it didn't necessarily come through the axes. Let me just, we don't know that. So it's going to be at 2, 0, and it kind of goes like that then, because that's moved it 5 to the right. And then this only affects the y coordinate. If you like, it doubles all y coordinates, but the y coordinate here is 0, so double 0 is 0. But up here, we're going to get b is now, well, let's increase minus 1 by 5. We're going to get 6. And sorry, one of these I've added wrong. I increase that by 5, you get 2. Increase that by 5, you get 4. Oh dear. And then we need to double the y coordinates, which gives you 8. There we go, and that's where B is. I assume they want us to show where B is now. Part B, so yeah, that one, well, we need to move it up 8, and also we need to stretch it by scale factor minus 3. Let's build this up slowly, yeah? F of x is here. F of minus 3. Once I do the minus 3x, I'm going to do this in 2 goes. First, I'm going to do minus 3 f of x, yeah? Well, that's where we stretch, well, multiply all y coordinates by minus 3, essentially. And so what's that going to do? Well, it's going to turn it upside down and reflect it in the x-axis. So you're going to have, not very good graph, it touching there, but B, we're now going to have that at like, and it's not very shown very well on my diagram, it's not going to change the x coordinate, but it's going to change the y coordinate. So you multiply it by minus 3. So that's now going to be minus 12. And this one's going to be minus 3, 0. But now we've just got to increase the y coordinates by 8. So that's going to be minus 4 in the end. And that's going to be actually up here at 8. It's going to move the whole thing up 8. So let's now move those up. We're now going to have, let me just draw a general shape. We're now going to have minus 3, 8 for A. And B, and it doesn't look very good on my diagram because I haven't drawn it very nicely, but it's actually going to be at minus 1, minus 4, because the previous value was minus 1, minus 12, and we need to move it up 8. So that's going to give us minus 1, minus 4. Oh, why does it keep doing this sinking thing? It's quite annoying. We're just on the last question. I've almost finished. So this one is actually minus 1, minus 4. And it's because we were at minus 1, minus 12 before, but we increased it by 8. Okay, this last one, worst one of the lot, it really is. Because you're working inside the brackets, you have to remember that you're not really doing bib maths, you're doing samdib. So it's awkward, definitely. Essentially, if you start with f of x, we're first going to change that into y equals f of minus 3x. Now, what does that do? Firstly, it reflects it in the y-axis and squashes it by a factor of 3. Or if you like, it times this all x coordinates by minus 3. But I do like to bear in mind it's being reflected. So if I can just pick that picture up, you have to do the stretch before the translation here, which feels counterintuitive in some ways. Okay, right. So what's that going to give me? I'm doing this in a bit of a weird way. It's the hardest one. It's definitely a really difficult one, this one. You're going to come down here, go up there, and then kind of go off. Now, that's affected the reflection. You're going to be multiplying all x coordinates by minus 3. So this is now going to be at 9, 0. And this is going to be at, now what have we done with the x coordinates? Times them by minus 3. And so this is actually going to be at like a 3, 4. Yeah. Now it gets more awkward than this because now we've got to replace x with something which, after you multiply out the brackets, gives you a plus 1 on the end. Now I wonder if you can see that that's x minus a third, I think. Yeah. So what we're going to need to do here to go from here to here, because you always attack the x, that's the way I put it. when you're doing these kinds of questions. Can you see if I multiply that out, I'm going to get minus 3x plus 1. And minus 3x plus 1 is what I'm trying to draw here. So what have I got to do? I've got to basically move all x coordinates to the right by a third, yeah? And so that's going to give me a similar looking graph. But that's going to be 9 plus a third, which is like 28 over 3 and 0. And this one's going to be 3 plus a third, which is 10 thirds and 4. Now, there are different ways of looking at that one, definitely. There are different ways of doing that, without a doubt. Let me just see, actually, because I'm kind of convinced that I've done something wrong there. Oh, yeah, I have. Yeah, yeah. Can I do this one again? I times these by minus 3 when I shouldn't. I should have done the opposite. I should have divided them by minus 3. Let me start again. That's the last one's a real, honestly, it's really tricky, these ones. I tell you what I normally remember if I'm doing something like this. I just remember if you've ever got the really awkward one, which is where you've got f of ax plus b, yeah, then you need to do it backwards. If you've ever got f of ax plus b as a transformation, this is basically not stretch then translate. The best way of looking at this is translate by 0 minus b, oh, sorry, minus b0. Doing this the wrong way around now, I'm messing up everything. Yeah. At least you can see this last one's tough. Yeah, it is really tough. Minus b0, and then stretch by scale factor, actually squash, that's what I did wrong before. Squash scale factor a. Yeah. Now, how do I know it works like this? Well, consider y equals x squared and y equals 2x minus 1 all squared. Yeah, because everybody understands that. Because everybody knows that 2x minus 1 squared hits at a half. Yeah. Well, if you thought, oh, I need to stretch it by scale factor 2 or squash it by scale factor 2 first and then move it to the right 1, this wouldn't be at a half, it would be at 1. And that doesn't make any sense. That's why we definitely need to move it 1 to the right first, then squash it scale factor 2. Yeah. So let's use a similar principle here, but we've got minus 3x plus 1. So we're going to use a similar principle with minus 3x plus 1. We're first going to move that graph 1 to the left, which puts it at minus 4, 0 and minus 2, 4. Yeah, that's after I've moved it 1 to the right. And then next, I'm going to squash it, compress it, if you like, scale factor minus 3, yeah, which has the effect of dividing all x coordinates by minus 3. Now, what's that going to do? That's going to move it over here, like this, minus 4 divided by minus a third, well, sorry, yeah, minus 4 divided by minus 3 is going to give you 4 thirds, 0. And then minus 2 divided by minus 3 is going to give you 2 thirds, and the y coordinate will remain unchanged at 4. There are other ways of thinking about that, but this is probably the easiest way of doing it. I wouldn't mind showing you what I was thinking about, though, in my head earlier. When I'd said, okay, I'm going to do minus 3x first, what I should have done, my mistake was I should have divided everything by minus 3. So just to show you could do it the way I was doing it, minus 3 divided by minus 3 is 1. Minus 1 divided by minus 3 is a third. So it should have gone to 1 a third, like this. Let's get it right the way I draw it. So this would be 1, 0, and this would be a third, 4. And then we need to go to f of minus 3 times by x minus a third, just so it works out as minus 3x plus 1. And that corresponds to moving it 1 third, place of 1 third to the right. And that's why you get the same answer. I just wanted to show you can kind of think of it in 2 different ways: 4 thirds, 0, and 2 thirds, 4. Yeah, very difficult, that last one, easily messed up in exam conditions. Okay, thanks for listening. Well done, and I hope it was useful. Bye-bye.